Okay, carbohydrates. Every diet under the sun says avoid carbohydrates, but how many people actually know what they are and have some idea as to why they make weight control hard or whatever, and certainly control of things like diabetes. We're going to look at a few things. First of all, we're going to classify monosaccharides, what an aldose is, and a ketose. So I'm going to introduce a couple of functional types of carbohydrates. Going to go into the concept of chirality. And within chirality, we will be able to determine the difference between D and L enantiomers. We'll come back to the word enantiomers probably tomorrow. Look at Fisher projections, okay, which are pretty straightforward. Haworth projections, however, are notoriously sticky concepts. So I will drill down on Haworth projections a bit more tomorrow. Yeah, redox reactions of monosaccharides. I'll just briefly touch on that. I don't find that all that actionable, certainly for the dental hygiene students. And the associated concept of reducing sugars and how monosaccharides link to form disaccharides and polysaccharides, starches, cellulose, other types of things are just chains of monosaccharides. Okay. So carbohydrates is a major source of energy in our diet. Here we have a lovely starchy food, breads, potatoes, pastas, all the fun things. They're supposedly bad for us, but they are the fuel. Without carbohydrates, we wouldn't be able to function for very long whatsoever. It's just too many of them that causes the issue. Okay, so like I said, the first thing I'm going to look at with you is a monosaccharide and the difference between an aldose and a ketose. Okay, you may not know what those mean in a moment, but you will by the time that you log off today. Okay, so carbohydrates are produced. Well, let's go back to our chemical reaction and see here we have carbon dioxide plus water plus energy from photosynthesis. So energy from the sun gives us carbohydrates, in this case, the stereotypical monosaccharide glucose, and oxygen comes off. And notice if we run this thing backwards, and it says respirations on the slide, that should look familiar. Okay, it's combustion, right? So kind of the opposite of photosynthesis, making carbohydrates. No surprise if you're breaking down organic molecules like we studied in combustion. It's just called respiration is just a special form of combustion. Let's see. Did someone have a question? Thought I heard. Oh, what do we have here? Okay, great. Thank you for letting me know about that. All right, so photosynthesis, making of carbohydrates, respiration is a combustion which we all participate in just by virtue of being living, breathing mammals. We are combusting carbohydrates and releasing the energy that we use for our metabolic processes. Okay, breaking those bonds. Okay, so there are three types of carbohydrates. Monosaccharides, there's one. Okay, disaccharides, of course, with two, and polysaccharides is three or more. And as they get up into hundreds and hundreds of linkage, we get into starches and glycogen and other starches, as well as cellulose. Okay, so aldehyde and ketones. Okay. So just like we saw the distinctions in our introduction to organic chemistry, you can start modifying the carbon hydrogens with double bonds, triple bonds, and you can start tacking things in there. So in organic chemistry, we saw things like bromine being chlorine being added, and more importantly for today's topic, other carbohydrate side chains. Okay. So aldehyde is a special um, construct that involves, over here in pink, a carbon double bonded to an oxygen and a hydrogen, and then the other is to another carbon down to the rest of the molecule, in this case going down off the page. So what you're looking for with an aldehyde is a carbon to oxygen double bond and hydrogen at the terminal end, at the end of a it doesn't have to be a monosaccharide, but any carbohydrate. But in this case, it's a monosaccharide. So that is an aldehyde. Okay. And they're important chemically for reasons that you won't really have to know unless you take organic chemistry a little deeper, why aldehydes are so important. The other major type that we have is also involves a double bond to oxygen, but it is not on the end of a carbohydrate. So I'm just going to redraw this in the expanded form here. CH2 to OH, the ketone, and then we have chains going down, dot, 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 down the page in that case. So what we're looking for something that identifies as a ketone, again, we have that double bond, but that is not at the terminal end like we have here with the aldehyde. Okay. Yeah. Nope. By definition, yes, you have a double bond to oxygen and a single bond to hydrogen at the terminal end of a carbohydrate. Yep. And then a ketone, that carbon to double bonded to oxygen can be anywhere. I mean, let's take some of this stuff out of here. And we'll just move it down one. There we go. We still have a ketone, but just the oxygen is bonded to a different carbon than it was in my previous example. Okay. Okay, so ketones, aldehydes. Okay, let's stick there for now and look at classification based on the number of carbons. Let's see if I can get a little fancy here. Based on the number of carbons. So triose has 3 carbon atoms. Tetrose, 4 carbon atoms. Not super. Now, once we get up to pentoses and hexoses, we start seeing the things that we use as energies, okay? With the 5 carbons and the 6 carbons, okay? And so an aldopentose, for instance, would be a 5 carbon saccharide, okay, or carbohydrate with an aldehyde group. So we'd have 1, 2, 3, 4, 5. So we know it is a pent. Oh, did someone just show up? Huzzah. We got Brenda. We have a pent, and then it says an aldehyde group. So here is our aldehyde group right there. And then so you have a aldo for aldehyde, pentose. Okay. That is the monosaccharide. And I left the hydrogens and other things off of there. Okay, so a ketohexose, okay, hex, 1, 2, 3, 4, 5, and 6 with a ketone somewhere. I'll just put it right there. There's a ketone. So that is a ketohexose. Monosaccharide that is a ketohexose. That's all they're saying. Fancy words that just mean something pretty straightforward. Okay, aldopexose. And of course, you could have an aldohexose. You could have ketopentose, etc., depending on whether you have the aldehyde or ketone on there. Okay, so let's look at a few examples here. So we have 3 carbons. That is an aldo because it's got an aldehyde, aldotriose. Okay. Again, we have an aldehyde. We have 1, 2, 3, 4. So aldotetrose in the second case. Next one over, aldopentose. 1, 2, 3, 4, 5. 5 carbons with an aldose on the end. And a ketohexose, like the one I just drew, right? Over here is a ketohexose, of which fructose is an example of a ketohexose, a monosaccharide, 6 carbons, and a ketone. Okay, so you guys tell me, is A, what type of a monosaccharide do we have on the left-hand side there? Okay. You know, so that functional, well, what? Actually, it's hex, 1, 2, 3, 4, 5, 6. So we do have a hexose. And then on the end, we have an aldehyde, aldohexose. Okay. And in the second case, we have 1, 2, 3, 4, 5. There is our pentose, example B. And a ketone, that carbon double bonded to oxygen. So that is a ketopentose. Okay. Example right there. So let's take a quick detour here away from these naming of sugars and take a look at chirality, because it is an important thing, certainly in pharmacy, because, and I'll explain why when we get to it here. So when we're talking about chirality, we're talking about chirality, also called handedness. I mean, like your left hand and your right hand are chiral because you can't, let's see, where's my camera? You can't superimpose your hands on top of each other. Your thumb is always on the wrong place. If you take the mirror image and try and get it to go on there, it won't fit. That's what chirality is. Okay, something is achiral if you can superimpose them on top of one another. What would be something that would be chiral? There, a couple of paper clips. Okay, we have mirror images of the paper clips. Everything's moving backwards. Okay. And so the mirror image of that one and that one, you can rotate around and superimpose them on top of one another. So they're indistinguishable. The mirror images are indistinguishable from one another. And those are what are called achiral, if they are superimposable like that. Okay. That's the idea behind it. And then we just do it with molecules, and that makes chemistry. But handedness is all throughout our lives. Okay, and those are called even the mirror images of a molecule are called stereoisomers. Okay, means that they are chiral. They're non-superimposable, even though they have the same same chemical, same atoms in them. Okay. And I'm going to come back to structural isomers. So chirality, mirror images, superimposable, non-superimposable. So a pair of gloves, chiral. A pair of shoes, also chiral. There's handedness. A pair of baseball bats is the example they use here. You can totally take the mirror image of a baseball bat and superimpose it on itself. Okay? So that's the basic idea on chirality. Now, when we're looking at organic chemistry and chirality, what we're looking at, we have a chiral center anytime we have a carbon that is bonded to 4 different groups. That's what makes something chiral. And I'll show you why. So for instance, if we had carbon bonded to bromine, chlorine, hydrogen, and another carbon, that's 4 different things for each of those bonds. That creates a chiral center right here and a subsequent chiral molecule, okay, that has handedness, okay? Now, if something had, let's say, a bromine, another bromine, a hydrogen, and a chlorine, this would be achiral because you have 2 things right here in bromine that are the same. So the mirror image are going to be superimposable on one another. If that doesn't make sense at the moment, let's look at what that actually looks like. Okay. So here we have a carbon in the middle bonded to bromine, chlorine, iodine, and hydrogen, and directly across from it, the mirror image. No matter which way you turn those 2 carbons around, you'll never get them on top of each other. Like the bromine will be on top of the chlorine, the iodine will be on top of the bromine. They'll just never line up. So you have a chiral molecule in that case, okay? And they are enantiomers, and they are stereoisomers that cannot be superimposed. Okay, stereoisomers, they have that, they are chiral. Stereoisomers that cannot be superimposed are enantiomers. Enantiomers are stereoisomers that have a chiral center, and you cannot superimpose the molecules on top of one another. Okay? Now, if you have an achiral molecule, such as this, here we see we have 2 bromines. Mirror image, you can very easily, in this case, they rotated the one on the right and make it as indistinguishable from the other one. So this would be an achiral molecule. Okay, chiral have handedness, are not superimposable. They are enantiomers. Achiral carbons are indistinguishable. Okay, so they are superimposable. Okay. Okay, so let's take a look here. Is a chiral atom or not? It is chiral because you have four different things bonded to that carbon. You have a chlorine, a methyl group, an ethyl group, and a hydrogen. Okay, four different things, chiral. Okay, in B, you can see we have a chlorine, a methyl group, and two hydrogens. The two hydrogens makes it achiral. Okay, and in the last case, we have a chlorine, a methyl group, a bromine, and a hydrogen. And we're back to chiral in example C. Okay, chiral, achiral, and chiral. Okay, enantiomers are stereoisomers that are chiral. A lot of big fancy words, but hopefully the concepts are kind of self-explanatory. And I'm going to go back. Let's see here. No, I'll look at structural isomers tomorrow. I don't want to introduce that concept today, since I'm just on such a roll with chirality here. All right. So this is where this is to be the last thing that I kind of look at first of all. Okay. Are Fisher projections, and I'm just going to introduce the idea of Fisher projections, and we'll get a lot more into this tomorrow. Fisher projections basically run from top to bottom with the aldehyde or ketone located at the top, running down to the furthest away from that. Okay, 1, 2, 3, 4. So we have an aldo tetros there, and a 1, 2, 3, 4. Yeah. And what we're talking about here on these Fisher projections, okay, let me just draw 1, 2, 3, 4. Our aldehyde up top, hydrogen to the right. Hydroxyl off to the left with a CH2 on the bottom. And they just wrote CH2OH. Okay. So to assign left and right, or L and D enantiomers of this sugar, what you want to be looking at, I left off the most important part, is this carbon way down at the bottom of your Fisher projection. Okay? So once you locate this functional group up top, go to the opposite end, look at the last carbon in the chain and where this hydroxyl is. Okay? The hydroxyl is either going to be on this side or this side. In this case, it's on the left-hand side. So that makes this the D version. Or excuse me, the L version on the left-hand side. Oof, another cup of coffee. The L version of this monosaccharide. Okay? If this was over here, we would have the D version. So levorotatory, L for levorotatory, D for dextrorotatory. So easy way to L for left and D for dextrorotatory. Okay, easy as that. So identify that functional group and look for the hydroxyl on the last carbon that has a chiral center, right? So you can see, and this is chiral because we have a hydrogen, hydroxyl, down there. Okay, so let's see if you guys were following along. Is example A the D or L version of that molecule? Well, the hydroxy is on the right. That's the D. Okay, and in example B, that is the on the left-hand side, so that is the L version. Okay, D on the right, L on the left. Okay, so the hydroxyl is on the left in the second case, and on the right in the first case. Hopefully, fairly straightforward. I'm hoping. In this case, okay. And now you guys say, so what? So something is non-superimposable, and why do I care? Well, you care because if you remember from anatomy, and I know because I talked about receptors on the surface of cells, right? Floating around in the fluid mosaic surface of the cell, there's receptors. So oftentimes those receptors will only fit lock and key with either the D or L versions of a drug, for instance, or only certain versions of a carbohydrate are digestible. Okay. D might be digestible because the enzymes that break it down only work on the dextrorotatory form of something. So it all comes down to the lock and key fit into enzymes. Okay. And there are some drugs that are mixtures of D and L versions of something. And we are getting to the point where we can get just the active version, and then we can cut the dose in half and cut down on side effects and all kinds of things. So it's kind of a cool thing to look at. Okay. And that's what we're looking at there. Enantiomers with enzymes or receptors. So either the D or L is the only fit for enzymes and receptors biologically. Okay, so you cannot get the second version on the right to fit. Okay, can't get square pegs into round holes, right? You can only do it when you have the version on the left to fit into the enzyme. Okay. And you know what? Let's pick up with that. How are we doing on time? That idea tomorrow. I'll go back and we'll hit this again. Planted the seed. So, as per usual, what I would like you guys to do is go ahead and do your homework for today, which is the quiz inside of Blackboard, something you learned today. I'm assuming you learned something. Or if you have questions you'd like me to address in class, put those in there so I can take a look at them. If there's no answer in there by 11:30, I'll send you a little tickle to do that. And that is it. So you are free to log off this point if you don't have any questions, and I'll see you in class tomorrow. And if you do have questions, stick around and I'd be happy to go over those with you. Oop, and let me